So for our final short course talk, I'm delighted to introduce Geraint Jones from University College London, professor of planetary science, cometary and small body science expert, including solar wind interactions. And Geraint is also the mission proposal lead for the ESA Comet Interceptor mission. And so that's what he's here to talk to us all about. We're really looking forward to your presentation. Welcome.
Great, thanks very much, Jim, and hello everyone. Yeah, so I'm going to talk about a rapid response mission that is happening. Since June, we know for sure that ESA are going to go ahead with this mission. So I'll spend the next half hour or so explaining how it came about. And the conveners of this workshop sent a few questions to address. So I'm actually, they were very reasonable questions, so I've based the presentation around that. So some of the material I'll show is from the definition study report, which has many co-authors, both from the proposing team, but also from ESA, with some inputs from industry as well. So first of all, just to recognize the group behind this mission. So I've been working most closely with Colin Snodgrass at the University of Edinburgh and Cecilia Tobiana at IAPS in Italy, and with now over 300 others. It grew from the first proposal to right now, and this is the group meeting we had back in July of 2022. So the first question that was put forward was what led to Europe funding Comet Interceptor, and what lessons can we take away from that process? Comet Interceptor also has a very significant contribution from Japan as well, which I'll describe in a few minutes' time. But this is what kicked everything off. So ESA issued a call for mission proposals. This came out in July 2018. And you can see towards the bottom here, they gave approximate limits for this mission to have a wet mass of less than 1,000 kilograms, to be launched to Earth-Sun L2, to be co-launched with either Ariel or Plateau, but the Plateau co-launch was dropped. So whatever was to be proposed to this would be delivered to L2 from the outset. That was the definition of the call. So whatever was to be proposed by the scientists submitting proposals, that had their spacecraft had to go to L2 first. So there are also cost caps on that as well. So the maximum cost to ESA at completion, excluding the launch, because it's being launched with Ariel, which is whose launch is paid for already. So that's 150 million euros. So one key difference between ESA science missions and NASA ones is that ESA generally don't fund the instruments that are on planetary science missions. So they're funded by the ESA member states. So the cost of the instruments themselves and the instrument teams are not included in this cost cap, but the cost of operating the mission and also building the spacecraft is included in that 150 million euros. So, as I said, it's after that initial call came out, it soon was defined as having to launch with Ariel to Sun-Earth L2. At the time of the call, it was to 2028. Now it's late 2029 when we expect both Ariel and Comet Interceptor to launch. So there was a two-stage submission process. There had been some feedback from other ESA calls that often people would submit very extensive proposals only to have them turned down very soon afterwards. So ESA responded to that criticism very positively and made a two-step proposal. So the first one was a very modest, short summary, and after those was sifted through, a limited number of teams were invited to submit a full proposal to phase 2. So after Comet Interceptor had passed that first stage, we met in London. There'll be a few group photos, but hopefully not too many. And at the Royal Astronomical Society, we were sort of inspired by the works of Caroline Herschel, etc., that are housed there in the library to work on this mission and put together the Phase 2 mission proposal. So I had the privilege of leading that. So it went in March 2019. We were then interviewed by the selection panel. And in June 2019, we had the great news that ESA had selected it for further studies. So critically, they hadn't given the full go-ahead, but it was the highest ranked of the F-class proposals. So the mission proposals that go into ESA generally don't have very strong support from industry. So unlike discovery proposals in NASA, for example, where industry will play a key part in designing the mission in great detail, on the ESA side, generally, there's only an outline of the mission proposal at the spacecraft side and operations, etc. So what then happens after the mission is selected on these outline plans, ESA then run a CDF study. So at ESTEC, in 2 phases during July to December 2019, the Concurrent Design Facility group met there, and those of us on the science proposing team were also involved in this, providing input to the engineers and navigation experts, etc., at NASA, at ESA, and they were verifying that the proposed concept was viable within the cost and mass constraints. And during that time, we had our what turned out to be our last in-person group meeting for quite a while in Spain, and then of course it hit us on the proposing team, ESA and industry, and everyone else in this room. We had to switch to working virtually over Zoom and other platforms, and worked on developing the instruments with support from the national agencies, working with the ESA project team to design the mission in more detail. And then earlier this year, at the beginning of the summer, we had the fantastic news that ESA had formally adopted the mission. So that means that the ESA member states all voted on whether to go ahead with this mission. ESA recommended that they do so, and the member states did vote to give the go-ahead. So Comet Interceptor is now definitely happening with launch plan for 2029. And so this screen grab from Deep Impact might now become true. So to address the question, what led to Europe funding this? So Comet Interceptor was proposed in response to the F-class call, which was going to L2 anyway. And through informal feedback and some reading between the lines, obviously it was found to be viable, groundbreaking, and scientifically valuable. But also another aspect which hasn't really come out is the fact that it wouldn't affect the Ariel launch. So because we weren't going to a particular known target, there was no constraint imposed on the launch of Ariel, the mission that we'd be launching with. Okay, so next question is what architecture decisions led to Comet Interceptor as it is today. So I'll just show a few slides based on how we've been presenting the mission to the science community and others over the past few years. So it's a mission targeting a long period comet, preferably dynamically new, or an interstellar object. So the chances of going to an ISO are obviously very, very low. We'd have to be extremely lucky to be able to get to one, but the possibility is non-zero, so we always do mention it as it's such an exciting prospect. So building on what Karen said at the beginning of the talks this morning, all the previous comet missions have been to objects that have passed the sun many times. So these comets have changed over time. They're also covered in a thick layer of dust from the backfall of dust, which doesn't escape the nucleus completely. And if we can get to an LPC, which is dynamically new, then that would be an extra bonus as well. We'd be seeing one of these objects nearing the sun for the first time, and these objects are pristine or as pristine as we can observe now. So you're all aware of the concept now. So we wait in space. So the mission is designed, built, sent to L2, and it waits at L2. So because it's not as stable as L4 and L5, you do need station keeping every 2 to 3 weeks or so, just to keep it in halo orbit around L2. But basically, we just wait there. There are no active operations planned for the spacecraft during the wait at L2. There is a pretty significant chance of finding a target before launch, so maybe we'll launch knowing where we're planning to go, but the mission obviously can also wait at L2 for several years as required if we don't have a target at launch. And then we can depart from L2 6 to 12 months after target discovery if we don't have a target before launch. So also, as has been mentioned earlier today, the only way to encounter a long period comet is to find one coming inbound very early, and with the advent of Vera Rubin imminent, this will increase the distance at which comets are discovered inbound as well. So this is just to stress that even with advanced warning, it's still not enough time to plan and build a spacecraft, so we do need the mission up in space ready, ideally, as well. So just a few cartoons to show what the mission concept was like. So the grey ellipse is Earth's orbit, so we leave Earth and go to L2, to a halo orbit, and we can wait for up to 3 or 4 years for our new target discovery if one isn't known beforehand. And obviously the search for comets takes place from the surface of the Earth. So routinely, comets are obviously all, their orbits are calculated from observational arcs, and we work out where each comet is going to cross the ecliptic plane. So we won't have enough fuel to go significantly north or south, so this has to be a flyby mission in the equatorial plane. And if we find a target that we can reach, then we wait for the correct phasing of the orbits, and then we depart L2. And as the comet nears the sun, its dust and gas tails are expected to grow, and then we have a flyby at the point of interception. So targets like this are being found. So there are a couple of examples there found last year and this year. So if Comet Interceptor was in space already, then these are objects that we could have traveled to if we had enough lead time. So there are many challenges, of course. So because long period comets basically got an isotropic arrival direction, we're just as likely to encounter a retrograde orbiting comet as a prograde one. So the encounter could be higher than 70 kilometers per second. And as we've heard before, so the Giotto flyby at Halley was at 68 kilometers per second. The Vega 1 and Vega 2 Soviet-led missions actually were at around 80 kilometers per second because they'd arrived at Halley after dropping balloons at Venus beforehand. So their different trajectories meant a higher flyby speed. All 3 of those spacecraft did survive. Giotto was damaged, but we took the 70 kilometer per second speed for the Halley encountered by Giotto to be a sort of an upper limit to what the mission would be designed for. Also, we can't predict our path through the comet, so the dust shield obviously has to be facing in the direction of travel, which might mean that we can't communicate with a high data rate with the Earth during the encounter itself. And the cost limit means that the entire mission will be shorter than 6 years in duration. So to address some of these, that yes, there'll be limited radio communications during the encounter itself. The dust shielding will be equivalent to Giotto. So Giotto got to about 600 kilometers of the nucleus of Halley at 68 kilometers per second. The wait at L2 is limited to around 3 years. So after being there for that long, we'll have to take a decision on where to go. And if we don't have a long period comet to go to, we do have a list of short period comets as well, which obviously wouldn't be as satisfying to go to, but some of the instruments we're carrying have not been taken to comets before, so there would be new science performed. So this is a multi-spacecraft mission. So the main spacecraft would be provided by ESA. So the flyby distance would be roughly 1,000 kilometers. And instruments such as the primary science camera and the mass spectrometer will be on that platform. And then there are two small probes, B1 and B2. So B1 is provided by JAXA, and B2 is second ESA craft. So A and B1 are three-axis stabilized, but B2 is actually spin stabilized like Giotto was, which allows sweeping of the sky by instrument to look at the scattering of light by dust in the coma. So the approach we took from the outset, and we tried to stress this in the proposal, was that this is a high-risk, high-gain approach. So obviously it would be best if both probes do survive the encounter and take data all the way through the coma. But if we lose one or both, then that's an acceptable risk that we stressed in the proposal. And actually, during the CDF study, many of the engineers were flagging this, saying, "Are you sure?" Because naturally the approach is to be risk averse, and actually being willing to lose one or two of these probes was understandably quite unusual. So why do we want three platforms? So we want to separate the time and space variation of features in the coma. So one of the obvious things is getting multiple views of the nucleus from slightly different directions. But also, as you'll see when we get to the instrument complement, we're looking at the solar-wind interaction as well. So if you just have single point measurements or along one track through the coma, you're only measuring the solar wind interaction along that one line. If you have two or ideally three tracks through the coma, then you can understand the solar wind interaction in 3 dimensions much more fully. And same goes with the dust detector as well, which will be on 2 of these 3 platforms. So we separate the safe and distant measurements from spacecraft A with high risk, high gain close approaches of the 2 small probes, both of which are around 30 to 35 kilograms in mass. So this cartoon shows you what the flyby will be like schematically. So the 2 small probes will go closer to the nucleus than the main spacecraft, and they'll be streaming data in real time to the primary spacecraft. So all the data that B1 and B2 collect will be transmitted as soon as possible to spacecraft A. So if anything happens to either or both of them, their data is safely stored aboard spacecraft A. And then after the encounter, the high gain antenna is pointed towards the Earth, and then we have data transmission covering weeks or even months, if necessary, after the encounter to get all the data down to Earth. So as, for example, we saw with New Horizons at Pluto. But the key observations all take place within a very short period, so they happen within a few days. So the timeline of operations, so there will be some variations to this based on the flyby speed, and maybe adjustments to the flyby distances depending on activity level, but the baseline is 1,000-kilometer flyby for the primary spacecraft. So the 3 spacecraft stack will first be pointed towards the nominal trajectory for the B1 probe. That will be released, and then the spacecraft A and B2 still attached to each other have a divert maneuver to put them on the trajectory for B2. And then after B2 is separated, the primary spacecraft A, then diverts itself to the 1,000-kilometer miss distance. So looking at the statistics for long-period comets, this is the distribution of possible encounter velocities and solar aspect angle. So you can see, yes, we could go over 70 and even beyond 80 kilometers per second, but the spacecraft is being designed for this sort of speed maximum, 70 kilometers per second. And you can see that the maximum is roughly 50 or 60 kilometers per second in this distribution. So that's the most likely range. And then with solar aspect angle, this peaks at around 90 degrees to the Sun-Comet line. So just briefly, I won't go through these in detail, but we have the design driver and the main implication. So the maximum launch mass is still very close to what was in the original call for proposal, so just under 1 metric ton. And because we want these multi-point observations, we have the additional probes included. So we wanted to, there's a bit of a balancing act here between maximizing the delta V available, which allows us to go to a bigger range of targets and hence increase the probability of reaching targets, and weighing that against, okay, that was an inadvertent, weighing that against the payload mass, basically. So obviously, if you increase the ratio of fuel to payload, you can go to more places, but you can do arguably less science. So compromise had to be reached there. And obviously the spacecraft had to be designed for that big range in flyby speeds as well. So yeah, one key thing is that we just have one chance to take all the measurements. So the cartoon I showed you had the spacecraft A rotating to track the nucleus. That's no longer the case. We have the dust shield pointing in the direction of travel, and there will be a periscope feeding the image of the nucleus and the inner coma to the primary science camera on spacecraft A, and the infrared mapping spectrometer will also have its own tracking mirror as well. So yes, obviously we need the dust shield, and then there are constraints related to the F-class mission call as well. So the spacecraft design, so again, a different approach to what happens in the US. So after ESA's CDF study, they summarized what they saw as the nominal spacecraft design and used this as the basis for a call to industry to study their own more detailed spacecraft designs. And so 2 consortia were funded by ESA to look at the designs. So one led by Thales Alenia Space UK and the other led by OHB in Italy. And just very recently, earlier this month, OHB Italia was selected to be the prime contractor. So they'll be responsible with their partners for building spacecraft A and probe B2, and our colleagues in Japan will be providing B1. So the overall dimensions for both of these designs was very similar, so about 1.5 meters on a side, so that's with the solar panels folded up. The wet mass including margins was below the limits that was assigned. And I've mentioned the spin stabilization of B2 previously. So the propulsion is chemical, but that's only on spacecraft A, so B1 and B2 don't have their own propulsion. The communications is S-band between the 3 probes, or sorry, 2 probes on the main spacecraft, and X-band with the Earth. So the anticipated data volume is expected to be about 200 gigabits. So to address the question that was posed, so because of the nature of the F-class call, it was a requirement to go to L2 from the outset, and it's the mass and mission cost cap limits that constrain the size, complexity, and duration of the mission. So the next question was, what are the limitations of Comet Interceptor, and how might we implement rapid response differently in the future? So I'm not going to spend very long on this, but just show a few key plots. So when leaving L2, obviously you can use the fuel on board the spacecraft to get to your target, but lunar flybys are also a way of gaining some extra delta V as required. And These two plots show the range of locations in the ecliptic plane that could be reached for a transfer time of 1 year to the target and 3 years to the target. So the yellow-colored ones involve lunar flybys, whereas the black shading is involving the delta V from the fuel carried on the spacecraft alone, and intermediate ranges are covered here where you fly by the moon and also use varying amounts of fuel on board. So this is in a frame with the sun and the Earth fixed, so you can see that we get quite far around Earth's orbit in this rotating frame if we have a 3-year transfer time. And also the influence on delta V on the mission duration. The influence of delta V and mission duration on the probability of at least one long period comet target. Obviously, the longer you spend in space, the more likely it is that you'll find a target that you can reach. And then these three different colors, more than three, these different colors represent the different delta V values depending on the amount of fuel to mass ratio of the spacecraft. So the minimum delta V requirement is 600 meters per second. So it's actually this orange line in the middle. So if we have a mission duration going all the way up to 6 years, it's over 70% chance of finding at least one reachable long period comet target. And ESA decided that those statistics were acceptable for this mission. So the final delta V value will depend on the performance of Ariane 6.2. So it's a new launcher. So the first launch is only last week they announced it will be about a year from now. So once that flies, we'll have much better constraints on the actual performance of that rocket. And the fuel tanks will be slightly oversized in case more fuel mass can be carried on board Comet Interceptor as well. So to address this question, the mass and delta V constraints does limit the number of reachable targets. So it's about 70% or just above 70% with the current delta V allocation. The thermal design of the spacecraft has been fitted to that range of reachable targets. So very approximately from about 0.7 AU out to about 1.3 AU. And the mass also, of course, limits the instrumentation, though the mission is carrying a very capable set of scientific hardware, not only to look at the target itself, but also the solar-wind interaction as well. And then obviously for future similar missions, more mass and more delta V would be great, and the payload as well. If you want to concentrate on just understanding the target object itself and not the solar-wind interaction, then obviously different decisions could be made about the payload. So the solar-wind study, the interaction between the comet and the solar wind, it doesn't really matter what type of comet it is. You're looking at pickup ions and things which are not particularly sensitive to whether a comet is short period, long period, or an interstellar object. But our proposing team had a strong representation from that community, and that's reflected in the payload of the instruments that we have on board. So coming to the instruments, so what instruments are on there? So in the context of European missions, we of course started with Giotto, spin-stabilized spacecraft with dust shield at the bottom, and the high-gain antenna tilted precisely for that encounter with Comet Halley on the 13th of March 1986, because we knew exactly where the Earth would be on that day. And then it had a second encounter with Comet Krigskala up in 1992, where it had to go through sideways, basically, with the dust shield not protecting it much at all. But it did survive that second encounter, but the camera, unfortunately, had been damaged at Comet Halley and revealed this fantastic set of images, which put together make the composites that we're also familiar with. And then we had Rosetta, of course, very ambitious and extremely successful mission that traveled alongside Comet 67P. I can't move my pointer. For several years, and Philae was landed on the surface, and then just before the main mission ended, the landing site of Philae was also discovered by my colleague Ceci Tupiana. So Rosetta was a huge success, but we saw big advances in cometary science. So the field of cometary geology became a much more sophisticated one. Many new morphological features discovered, etc. And they raised new questions. How pristine was this comet? The pits, terraces, fractures, etc. Are they primordial or more recent features? And which of those are evolutionary? Also earlier today we heard about cometary composition and looking at the isotopic ratios. So the D to H ratio, 67P, as we heard earlier, is the worst match to seawater we've measured so far at a comet. But that's just one object, and obviously what arrived at Earth was a mixture. So there are more. So the more samples we have of isotopic ratios, then obviously the more we can learn about the makeup of these fascinating objects. So the science objectives for Comet Interceptor are split into two groups. So the first in situ characterization of a long period comet, preferably dynamically new or interstellar, as mentioned earlier. And then the first simultaneous multi-point exploration of a coma and the nucleus. So between the two European platforms and the Japanese ones, we'll get multiple views of the nucleus and in situ observations from 3 locations as well. So the best resolution at closest approach should be of the order of 8 to 10 meters if we have a 1,000 kilometer closest approach distance. And that's at a high enough scale to look at some of these features that were observed at 67P, see whether they were, if they're present in more primordial objects as well, and to look at the surface composition as well, and the presence of surface ice. And for the solar-wind interaction, I won't dwell on this. As I've said before, we're taking measurements of 3 different locations. We learn about the distribution of dust in the coma and the solar-wind interaction, which I've mentioned a few times already now. But we'll also have multiple views of features such as the iron tail, which we have not been able to achieve very successfully in the past. So just to put the mission in context, in comparison with Rosetta, many people, including some on our proposing team, saw it as Rosetta Mark II, but it is approximately an order of magnitude smaller. So it's 10 years from proposal to launch, and the cost you can see is about 10% that of Rosetta, very approximately. And obviously we're just having a fast flyby rather than spending an extended period at the comet. So this is a summary of the payload. So Nick Thomas is leading the primary science camera on spacecraft A, called COCA, that's heavily based on the Cassis camera on ExoMars Trace Gas Orbiter. Neil Bowles and Antti Nasila are leading the Miramis instrument, which is going to take thermal infrared observations at the comet, as well as at shorter wavelengths as well in the infrared. We have a mass spectrometer also led from the University of Bern by Martin Rubin. So that's on the main spacecraft. So that is designed to survive the entire encounter, and because it has a high data volume as well, it's safer for it to be on spacecraft A than on a small probe. And then we have multiple sensors making up DFP, which stands for dust, fields, and plasma. So on spacecraft A, we've got an electron spectrometer, ion spectrometer, energetic neutral atom detector, and dust detector and radio instrument as well. And then a dust detector on both spacecraft A and B2 of matching design. And then on probe B2, which is the European small probe, we have an instrument called ENVIS, which is going to sweep across the entire sky, making polarimetric observations of the dust, the way that the dust in the coma is scattering light. Estonia are leading the small camera on this platform, and then we have a magnetometer and dust detector on B2 as well. Just very briefly, with the spin stabilization, we can map out the entire sky surrounding the spacecraft from probe B2. So we'll have lower resolution images than the one shown at upper left, but it demonstrates the concept. So rather than taking polarization observations in just one direction, we can cover the entire sky. And then on the B1 spacecraft, we have two cameras, a wide angle and narrow angle camera, which will complement the observations with the two cameras on A and B1, and looking at the nucleus from quite a different direction to those platforms. A plasma suite looking at the ion population around the nucleus and the magnetic field as well. And then finally, a Lyman alpha detector as well. So we'll be able to observe the emission from the hydrogen corona of the comet. So that should be observable from a large distance before we get to the encounter itself. So that was a very rushed summary, so apologies for not going through that in greater detail. But as you can see, a very interdisciplinary suite of instruments looking at both the nucleus, the coma, and the solar-wind interaction. So if all goes well, this might be what the spacecraft will see early next decade. So we'll have dust grains sweeping past at tens of kilometers per second, and the two small probes, smaller than this in the sky, I hope, closer to the nucleus. The mission will be unique. The first multi-point measurement of a comet and its environment. With the arguable exception of Destiny Plus, which is going to an active asteroid. This will be the first dedicated comet mission launched for more than 25 years by any agency, and hopefully we'll see the most pristine object to be encountered so far. So the proposing team I showed, the management of the mission, the scientific management is currently being reformulated, and so ESA are in the process of appointing working group members now that the mission has been adopted, and the project scientist at ESA is Michael Kuppers. And we've, just in the past couple of weeks, submitted a paper to Space Science Reviews, so hopefully in the near future there'll be a citable source for all this information. Okay, thank you.